In computing, floating point is the formulaic representation that approximates a real number so as to support a trade-off between range and precision. A number is, in general, represented approximately to a fixed number of significant digits and scaled using an exponent. The base for the scaling is normally 2, 10, or 16. A number that can be represented exactly as of the following form, where significand z base n, and exponent z. For example, the term floating point refers to the fact that a number's radix point can float, that is, it can be placed anywhere relative to the significant digits of the number. This position is indicated as the exponent component, and thus the floating point representation can be thought of as a kind of scientific notation. A floating point system can be used to represent, with a fixed number of digits, numbers of different orders of magnitude, e.g., the distance between galaxies or the diameter of an atomic nucleus can be expressed with the same unit of length. The result of this dynamic range is that the numbers that can be represented are not uniformly spaced. The difference between two consecutive, representable numbers grows with the chosen scale. Over the years, a variety of floating point representations have been used in computers. However, since the 1990s, the most commonly encountered representation is that defined by the IEEE 754 standard. The speed of floating point operations, commonly measured in terms of flops, is an important characteristic of a computer system, especially for applications that involve intensive mathematical calculations. Overview. Floating point numbers. A number representation specifies some way of encoding a number, usually as a string of digits. There are several mechanisms by which strings of digits can represent numbers. In common mathematical notation, the digit string can be of any length, and the location of the radix point is indicated by placing an explicit point character there. If the radix point is not specified, then it is implicitly an integer and the unstated radix point would be off the right-hand end of the string, next to the least significant digit. In fixed point systems, a position in the string is specified for the radix point. In scientific notation, the given number is scaled by a power of 10, so that it lies within a certain range, typically between 1 and 10, with the radix point appearing immediately after the first digit. The scaling factor, as a power of 10, is then indicated separately at the end of the number. For example, the orbital period of Jupiter's moon Io is 700528533500152,853.5047 seconds. A value that would be represented in standard form scientific notation as 7005152853504700001.52853547 times 105 seconds. Floating point representation is similar in concept to scientific notation. Logically, a floating point number consists of a signed digit string of a given length in a given base. This digit string is referred to as the significand mantissa, or coefficient. The length of the significand determines the precision to which numbers can be represented. The radix point position is assumed always to be somewhere within the significand, often just after or just before the most significant digit, or to the right of the rightmost digit. This article generally follows the convention that the radix point is set just after the most significant digit, a signed integer exponent, which modifies the magnitude of the number. To derive the value of the floating point number, the significand is multiplied by the base raised to the power of the exponent, equivalent to shifting the radix point from its implied position by a number of places equal to the value of the exponent, to the right if the exponent is positive or to the left if the exponent is negative. Using base 10 as an example, the number 700515285350470000152,853.5047, which has 10 decimal digits of precision, precision, is represented as the significand 1,528,535,047 together with 5 as the exponent. To determine the actual value, a decimal point is placed after the first digit of the significand and the result is multiplied by 700510000000000000000000005 to give 7005152853504700001.528535047 times 105, or 70051528535047000152853.5047. In storing such a number, the base need not be stored, since it will be the same for the entire range of supported numbers, and can thus be inferred. Symbolically, this final value is, whereas the significand is the precision, is the base, and is the exponent. Historically, several number bases have been used for representing floating point numbers, with base 2 being the most common, followed by base 10, and other less common varieties, such as base 16, and even base 3. A floating point number is a rational number, because it can be represented as one integer divided by another. For example, 7003145000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 is *101010 145,100. The base determines the fractions that can be represented. For instance, 1/5 cannot be represented exactly as a floating point number using a binary base, but 1/5 can be represented exactly using a decimal base. However, 1/3 cannot be represented exactly by either binary or decimal, but in base 3, it is trivial. The occasions on which infinite expansions occur depend on the base and its prime factors, as described in the article on positional notation. The way in which the significand and exponent are stored in a computer is implementation dependent. The common IEEE formats are described in detail later and elsewhere, but as an example, in the binary single precision floating point representation, and so the significand is a string of 24 bits. For instance, the number pi s first 33-bitter. If the leftmost bit is considered the first bit, then the 24th bit is 0 and the 25th bit is 1, thus, in rounding to 24 bits, let's attribute to the 24th bit the value of the 25th, yielding, when this is stored using the IEEE 754 encoding, this becomes the significand with after a left adjustment during which leading or trailing zeros are truncated should there be any, which is unnecessary in this case. As a result of this normalization, the first bit of a non-zero binary significand is always 1, so it need not be stored, saving 1 bit of storage. In other words, from this representation, pi is calculated as follows. Whereas the normalized significand's nth bit from the left, where counting starts with 1. Normalization, which is reversed by the addition of the implicit 1, can be thought of as a form of compression. It allows a binary significand to be compressed into a field 1 bit shorter than the maximum precision, at the expense of extra processing. Alternatives to floating point numbers. The floating point representation is by far the most common way of representing in computers an approximation to real numbers. However, there are alternatives. Fixed point representation uses integer hardware operations controlled by a software implementation of a specific convention about the location of the binary or decimal point. For example, 6 bits or digits from the right. The hardware to manipulate these representations is less costly than floating point, and it can be used to perform normal integer operations, too. Binary fixed point is usually used in special-purpose applications on embedded processors that can only do integer arithmetic, but decimal fixed point is common in commercial applications. Binary coded decimal is an encoding for decimal numbers in which each digit is represented by its own binary sequence. It is possible to implement a floating-point system with BCD encoding. Logarithmic number systems represent a real number by the logarithm of its absolute value and assigned bit. The value distribution is similar to floating point, but the value-to representation curve is smooth. Conversely to floating-point arithmetic, in a logarithmic number system multiplication, division and exponentiation are simple to implement, but addition and subtraction are complex. The level index arithmetic of Plenshaw, Olver, and Turner is a scheme based on a generalized logarithm representation, where greater precision is desired. Floating-point arithmetic can be implemented with variable length significand staticized depending on actual need and depending on how the calculation proceeds. This is called arbitrary precision floating-point arithmetic. Some numbers cannot be represented exactly in binary floating point, no matter what the precision is. Software packages that perform rational arithmetic represent numbers as fractions with integral numerator and denominator, and can therefore represent any rational number exactly. Such packages generally need to use bignum arithmetic for the individual integers. Computer algebra systems such as Mathematica and Maxima can often handle irrational numbers like or in a completely formal way, without dealing with a specific encoding of the significand. Such a program can evaluate expressions like exactly, because it is programmed to process the underlying mathematics directly, instead of using approximate values for each intermediate calculation. History. In 1914, Leonardo Torres y Quevedo designed an electromechanical version of Charles Babbage's analytical engine, and included floating-point arithmetic. In 1938, Konrad Zuse of Berlin completed the Z1, the first binary programmable mechanical computer. It uses a 24-bit binary floating-point number representation with a 7-bit signed exponent, a 16-bit significand, and a signed bit. The more reliable relay-based Z3, completed in 1941, has representations for both positive and negative infinities. In particular, it implements defined operations with infinity, such as, and it stops on undefined operations, such as. Zuse also proposed, but did not complete, carefully rounded floating-point arithmetic that includes and NaN representations, anticipating features of the IEEE standard by 4 decades. In contrast, von Neumann recommended against floating-point numbers for the 1951 IAS machine, arguing that fixed-point arithmetic is preferable. The first commercial computer with floating-point hardware was Zuse's Z4 computer, designed in 1942 to 1945. In 1946, Bell Laboratories introduced the Mark V, which implements decimal floating-point numbers. The Pilot Ace has binary floating-point arithmetic, and it became operational in 1950 at National Physical Laboratory, UK. 33 were later sold commercially as the English electric juice. The arithmetic is actually implemented in software, but with a 1 MHz clock rate. The speed of floating-point and fixed-point operations in this machine were initially faster than those of many competing computers. The mass-produced IBM 704 followed in 1954. It introduced the use of a biased exponent. For many decades after that, floating-point hardware was typically an optional feature, and computers that had it were said to be scientific computers, or to have scientific computing capability. It was not until the launch of the Intel i486 in 1989 that general-purpose personal computers had floating-point capability in hardware as a standard feature. The UNIVAC 1100 and 2200 series, introduced in 1962, supports 2 floating-point representations. Single precision. 36 bits, organized as a 1-bit sign, an 8-bit exponent, and a 27-bit significand. Double precision. 72 bits, organized as a 1-bit sign, an 11-bit exponent, and a 60-bit significand. The IBM 7094, also introduced in 1962, supports single precision and double precision representations, but with no relation to the UNIVAC's representations. Indeed, in 1964, IBM introduced proprietary hexadecimal floating-point representations in its system, 360 mainframes. These same representations are still available for use in modern Z architecture systems. However, in 1998, IBM included IEEE-compatible binary floating-point arithmetic to its mainframes. In 2005, IBM also added IEEE-compatible decimal floating-point arithmetic. Initially, computers used many different representations for floating-point numbers. The lack of standardization at the mainframe level was an ongoing problem by the early 1970s for those writing and maintaining higher-level source code. These manufacturer floating-point standards differed in the word sizes, the representations, and the rounding behavior and general accuracy of operations. Floating-point compatibility across multiple computing systems was in desperate need of standardization by the early 1980s, leading to the creation of the IEEE-754 standard once the 32-bit word had become commonplace. This standard was significantly based on a proposal from Intel, which was designing the i8087 numerical coprocessor, Motorola, which was designing the 68000 around the same time, gave significant input as well. In 1989, mathematician and computer scientist William Kahan was honored with the Turing Award for being the primary architect behind this proposal. He was aided by his student and a visiting professor. Among the x86 innovations are these: a precisely specified floating-point representation at the bit string level, so that all compliant computers interpret bit patterns the same way. This makes it possible to accurately and efficiently transfer floating-point numbers from one computer to another. A precisely specified behavior for the arithmetic operations. A result is required to be produced as if infinitely precise arithmetic were used to yield a value that is then rounded according to specific rules. This means that a compliant computer program would always produce the same result when given a particular input, thus mitigating the almost mystical reputation that floating-point computation had developed for its hitherto seemingly non-deterministic behavior. The ability of exceptional conditions to propagate through a computation in a benign manner and then be handled by the software in a controlled fashion. Range of floating-point numbers. A floating-point number consists of two fixed-point components, whose range depends exclusively on the number of bits or digits in their representation, whereas components linearly depend on their range. The floating-point range linearly depends on the significand range and exponentially on the range of exponent component, which attaches outstandingly wider range to the number. On a typical computer system, a double precision binary floating-point number has a coefficient of 53 bits, an exponent of 11 bits, and one sign bit. Positive floating-point numbers in this format have an approximate range of 10⁻308 to 10,308. Because the range of the exponent is -1022, 1023, and 308 is approximately log 10. The complete range of the format is from about -10,308 through +10,308. The number of normalized floating-point numbers in a system F is. There is a smallest positive normalized floating-point number, under flow level equals UFL equals, which has a 1 as the leading digit and 0 for the remaining digits of the significand, and the smallest possible value for the exponent. There is a largest floating-point number, overflow level equals OFL equals, which has B-1 as the value for each digit of the significand and the largest possible value for the exponent. In addition, there are representable values strictly between -UFL and UFL, namely, positive and negative zeros, as well as denormalized numbers.